So let's just go through the first step of the integration here to have an appreciation for what it's going to take. So we have 2 integral negative pi over 2 to pi over 2. All right, antiderivative, or well, I'll just write it again, 0 to cosine theta, and then r root 9 minus r squared dr d theta. So we get to have the pleasure of integrating that. So 2 integral negative pi over 2 to pi over 2. Okay, antiderivative. Don't need trig sub. Thank goodness we don't need trig sub because that's a basic U sub. If I were doing this, let me do it. I'm going to go a little slower. Since it's Friday, let's just take our time. I'm just seeing if you're paying attention. That's all. Okay, so if I were doing this integral over here on the side, I were just doing this as its own Cal 2 problem, I would make a U substitution of 9 minus r squared. du would be negative 2r dr. And to see, this again is kind of like, how did you learn this? Everyone's got kind of their own way that they were taught. And so I would rewrite this. I replace my r dr with this. I replace my 9 minus r squared with this. So my new integral becomes negative 1/2 root u and then du. So that's the u sub. Then I have to do power rule on that. So this is negative 1/2 times 2/3 u to the 3/2 plus a constant, but the constant's not going to matter. These twos cancel. And so that would be it. That's our basic U sub. So over here, our antiderivative is negative 1/3 9 minus r squared raised to the 3/2 evaluated where? Ugh. R equals 0. I don't mind that so much. But then r equals 2 cos theta d theta. That is going to suck. Do you see why that's going to suck? It's not so much that I have to put 2 cosine theta here and square it. It's that it's all of that to the 3/2. That's the part. Which I believe is why I set on this problem to just set it up. Hold on. Do not evaluate. Okay, but we're going to have the computer evaluate it. All right? Let's have the computer do it. Shall we go to alpha or Wolfram alpha? Let's see if we can do another double integral in here. So we're going to integrate. The outer one went from negative pi over 2 to pi over 2. The inner integral was r times the square root of 9 minus r squared. Oh, and it's dr. And it's from 0 to 2 cosine of t. I'm going to put t instead of theta. And then this is going to be dt 0 to pi. That should be it. Let's see when I hit enter what it does. So was that it? Negative pi over 2 to pi over 2, 0 to 2 cosine theta, r root 9 minus r squared dr d theta. Why are you changing your mind? What happened? Okay, yeah, decided to do more. So there we go. Right here. 8.58 is the volume that what? That was drilled out. This is not the answer to the question, though. The question is how much, what's the volume of the ball? So now what you need to do is find the volume of the actual ball and subtract this much. But that's easy because we have a formula for that. The volume of that is 4/3 pi radius, which is 3, pi r cubed. So you figure out what that is and subtract that number, and that's the volume of what's left. Okay? All right. That's it for that one. I believe on the take-home exam there's a problem like that one, if I'm not mistaken.
Yes, but it has instead of the sphere, it has an what is it?
A paraboloid?
Paraboloid, yeah.
Yeah, it's a paraboloid.
No, so definitely don't
I believe that on that one you can, let me double check that before, because I've accidentally given students a problem that's not,
able to solve.
well, not by hand. Let me just make sure the one that I gave you. It's like this one where we couldn't. What is the, do you have it with you or no? No? He has it? Okay.
He has it. He has it.
Let me just make sure it's.
It's him, officer.
Yeah.
Also, for some reason, it's from 12.1 to 12.5 to exam.
Yeah,
this, the
okay.
take-home exam.
That's doable. Well, not yet. We haven't talked about it yet. Yeah.
But let's do Wednesday. Huh?
Well, we still have 45 minutes.
Oh.
Remember, you signed up for a class that went from 2 to 5:30. Okay. So we have one more thing to talk about before we can go. And that is applications of double integrals. Now, there are many applications. I have to pick something, and so what I'm going to choose is this idea of centers of mass and moments of inertia. So, look, this is one of these sections where we're not going to get into any real theory on this. We are simply going to provide you with a formula, which is a lot of the way it works in physics and engineering, is that by the time you get to the problem, they're like, hey, here's the formula you use for this, right? So that's what this is about. So a lamina, when we talk about a flat sheet, right? A flat sheet that has some shape to it, this is what we consider a lamina. It's two-dimensional, even though there's thickness to this, right? This page has thickness. We're going to consider this a two-dimensional lamina. And we're going to talk about the density of this lamina at every point. So density of a two-dimensional object is going to be defined as its mass over its area. So if you took the total mass of this thing and divided it by the total area of this thing, then that would give you its density. Okay? Now this sheet here, I only need one of them, we would say that this has uniform density. Like, would you agree that this sheet of paper, like the mass at every point is pretty much the same? I mean, these are little fibers of wood, so it's not perfect, but we would say it pretty much has uniform density. Okay, so in Cal 2, you can actually go through and you can find the center of mass of something like this, as long as it's uniform density. What we want to be able to do is find the mass and center of mass of something that is non-uniform. So the density at each point is different. So maybe there's more mass concentrated in one area than there is in another. So what we do, and again, this is just going to be a very quick, brief run through it, is we take, let's say that somebody has given us the density at every point. So we know if you go to a certain point, I know it's density, I know it's density, I know it's density. Then what we can do is take an infinitesimal little patch, right? So imagine this is almost like the domain on the ground that we've been doing, and the height of the surface above it is measuring the mass at every single point. So all I have to do to figure out mass is take your density and multiply it times the area. So I just need to take some little infinitesimal patch, that's the area, and then take a point in there, figure out its density, multiply the two together, and that will give me the mass at that little patch, that little piece. And then what I want to do is add them all up. And if I can add them all up, then I'd have the mass of the whole object. So at the end of the day, it's this formula right here. If somebody gives you the mass of the density function, tells you the density at every point, then to figure out the total mass of the lamina, all you have to do is add up all the densities times the areas to give you mass, and you do that in both directions, which requires a double integral. So before, this was just some arbitrary function, right? F of x, y. But if that's a density function, then this thing has a physical meaning to it. It would be the mass of this. So we can also do this for something other than mass. If we have what's called the charge density, so let's say that this is a lamina that has some electromagnetic charge throughout the object. If we know the charge density at every point, then we can figure out the total charge on the whole lamina by just, again, adding up all the charge densities times all of the little infinitesimal areas, and then that'll give us the total charge on the whole thing. So two different physical meanings, mass versus total charge, same integral, same basic idea, double integral over the region, whatever your function is with respect to area. Now we'll do this one in a second. Now, after that, we can calculate what are called the moments. Sorry. I forgot to silence my phone. Can I answer? It's my daughter. It's her birthday. Okay.
Go ahead.
Hey, what's up, baby?
Hi.
Hello.
I just saw
Oh, yeah, that was a long time ago.
an hour ago.
Yeah, I'm almost done, baby. I'll call you in just a minute. Okay. All right, love you. She's replying to a call like from an hour or two ago. Okay. All right, so we have the ability, if we have a lamina, we have the ability to calculate its mass if we're given the density at every point. If we're given the charge density, then we can calculate the total charge. Then we get to this physics idea of something called a moment. Have you all heard this before? Moment? Okay, so when you have a lamina, we have a moment about the x-axis, moment about the y-axis. This is for a two-dimensional lamina. These two things called moments. And all they are, okay, all the moment about the x-axis is the product of the density function times the area. So this is the mass, right? So this is basically adding up the mass at every point times y. So what's that? Like physically, if you have a lamina, here it is, and you were to go to some point here, little infinitesimal patch, doing just that part will give you the mass at that point, right? Yes?
Yeah.
But what does multiplying by y then do?
Of all points above the
Yeah, it's taking that mass and somehow like scaling it by how far away it is from the x-axis, because isn't this the y-coordinate? So we're multiplying by the y-coordinate of that point, which somehow gives it some sort of relationship between it and its distance from the x-axis. And this is the definition of a moment. It is the mass times the distance from some axis. Okay? And then later on, this becomes the moment of inertia, which has to do with an object's resistance to rotation. But for now, the moment is this y-coordinate times the mass at that point. And what we want to do is we want to go to every single point on here, every little infinitesimal patch, calculate the mass times the y, mass times the y, mass times the y, do all those calculations, add them all up, and that gives you what's called the moment about the x-axis. Then you can do the moment about the y-axis, which is the same thing, except instead of multiplying by y, you multiply by x. So this time, you're measuring this distance from here to here, here to here, here to here. So you're taking that for each little patch, calculating the mass, multiplying by the distance from the y-axis, and that gives you the moment about the y-axis. All right? Now, you might ask, why are these computations important? Well, look at the way we denote them. Capital M subscript x is your moment about the x-axis. Capital M subscript y is your moment about the y-axis. The reason why those are important is because of the next formula. If you have a lamina and it has a non-uniform density, so the density changes throughout throughout the entire lamina, then you can find the center of mass. You can find exactly where this thing would balance. And to do it, you have to do a couple of computations. You have to calculate where the center of mass is. At that point, we call it x bar, y bar. And to do the computation for x bar, to figure out what that number is, what the x coordinate is, you have to do capital M subscript y. What's that? That's the moment about the y-axis, which is that double integral I just showed you a second ago, right? That's actually this one. That's this double integral. And divide it by little m. And what's little m? That's the mass. And the mass integral was something else. So really, this formula written out properly should be this. This is how you find the center of mass. You have to do two double integrals. The first double integral is your density function times x, and then you divide it by just the density function. You calculate that, and that'll give you just the x coordinate of your center of mass. To find your y coordinate, you have to do the moment about the x-axis divided by mass. So that's another two double integrals. So really, at the end of this all, if you want to find the center of mass of a lamina, you have to calculate three double integrals. The moment about y, the moment about x, and then the mass is the same for both. So it's three double integrals. All right? I'm good. These are all these formulas are in the book. Yes?
So the x bar,
Yes.
you have to, the numerator is
The moment about y.
moment about y.
Which the moment about y has x in it.
Yeah.
It's weird, right? It's confusing. If you want to find x bar, you have to take the moment about y, which in the formula has x. Yeah, see, because the moment about y is the distance from the thing to the y-axis, which is the x coordinate. So that's why it seems weird. We should do an example. At least we set them up, right?
Yeah.
Oh, did I give you all the picture? Do you have the test? I did give you the picture of that. Consider lamina. I did not give you the actual region. Yeah, I need to give you all that. I had a feeling I was forgetting something. Okay. Don't let me forget that before we leave. I have to give you something that goes with that. All right, so let's do this one. At least set it up. Find the center of mass of the region bounded by x equals 0, y equals x, and 2x plus y equals 6. So let's get the region first. X is 0, right? Y is x. And 2x plus y equals 6. So that's the same as y equals negative 2x plus 6, right? Solve for y. That'll help me graph it a little better. I go up to 6, and I know it has a slope of negative 2, so it's going to go something like that. So the region we're talking about is this region right in here. Right? So this is my lamina. And the density at every point is given by x squared. And I really don't like this example, so I'm going to change it a little bit. Let's do x squared plus 1. Do you know why I'm doing that? Why am I doing x squared plus 1? Because if it was just x squared, what's the density along this edge? What's the density at every point on this edge? 0, which wouldn't make a whole lot of sense, right? So if I go x squared plus 1, then I have defined, like I have density everywhere. Okay. So in other words, what's happening here is as we move out, our density changes, right? But all that matters is the x coordinate, because this is our density function, right? Okay, what do we need? What do we need? What do we need? Well, we need to know the mass, don't we? We need to know the mass. So the mass of this is going to be the double integral over d of the density function dA. Okay, so my density function is given, right? I just need to know the domain, and that's this region, which is the lamina itself, right? So what type of region is this?
That's going to be a good type 1.
Type 1, good old Cartesian type 1, right? We do need to know where these hit each other. I know this is 0, but where do those hit each other? 2? At x is 2? Yeah. I think it's at x. You can set them equal to each other, but you should be able to verify it happens at 2, right? So I know that my x is between 0 and 2. I know my y is stuck between these two functions. The top one is this one, the bottom one is this one. So x goes here, and then negative 2x plus 6 goes there. You following? And then my density function. So I should be able to fill this all in now. We got 0 to 2. We've got x to negative 2x plus 6. I'm integrating my density function, x squared plus 1, and I'm doing this with respect to y then x. There we go. That's our mass. Could you integrate that with respect to y? Yeah? And plug in these two things? It would suck. And then integrate that with respect to x? That would suck. And then you evaluate 0 to 2. All right? So let's cheat. Now, I'm expecting that on these take-homes you're doing these, right? These are take-homes. I'm only doing this to illustrate the answer. Okay, so I'm integrating x squared plus 1. I'm doing that with respect to y. And I'm doing that from x to negative 2x plus 6. And then I'm integrating that with respect to x. I'm doing that from 0 to 2. So after about 30 minutes of work, you should get that the mass of this is 10. Okay, nice. It works out to be a nice clean number.
Yeah.
10 whatever. We don't have any units right now. All right. Now, let's do the moment about the y-axis, which I'll need. I need the moment about y to get x bar, right? So what's the difference between the formula for moment about y and mass? There's only one difference. You still do d. This now becomes x density function. Okay? It's the only difference. And so when you do this double integral, everything stays the same. Did I do that backwards? Hold on. No. I just wrote it backwards here. X negative 2x plus 6. What's the only difference now? This is no longer this. It's what? This times x. So this becomes x cubed plus x dy dx. And of course, that's going to change everything when you do the antiderivative, which is going to suck again going through that, except if you do it this way. Because here all you do is x cubed plus x, and nothing else changes. So I get 8.8. Okay? right with that? Let's go ahead and get the moment about x. What's the moment about x? Well, that's double integral over d, but instead of putting x here, what am I going to put? Y. So y times x squared plus 1 dy dx. Or sorry, dA. Let's go dA. And you put your limits of integration, same thing. So now when you integrate this with respect to y, it's going to not be that great. Are you following what I'm doing here? Okay, so I'm going to go ahead and go up here and change this now. This will now become y times x squared plus 1. I messed that up. $25.6. I'm ready to answer the questions. I'll leave the picture up there. We had the mass was 10, right? The mass was 10. The moment about y was 8.8. The moment about x was 25.6. So by definition, x bar is the moment about y over mass, which is 8.8 divided by 10, which is going to be 0.88, all right? And then your y bar is going to be your moment about x over mass, which is 25.6 over 10, which is 2.56. So in my picture, and it's not a great picture, but here's one. If I go to 0.88 and then I go up to 2.56, somewhere in here, 2.56 is a little bit, where do they hit each other? At 2.2? So 0.8, I don't know, somewhere around right in here is my center of mass. Now remember, this is a non-uniform density, right? What if it was uniform density? Then it should be symmetric, but what would change in our formulas?
You wouldn't have the density.
Yeah, this x squared plus 1 would just be 1.
Yeah.
Uniform density, everything's uniform, right? So, okay, so now on the take home, I gave you a problem and I gave you a graph and I forgot to put what the graph of that was, right? That is e to the x. So this is number 4? Number 6?
Yes. There's
Yeah. So on that one, yeah, I give you this graph. So number 6 of the take home, it goes from 0 to 1, and it's e to the x. And because it's my daughter's birthday, and because this is due in 2 days, I will let you use the computer to get the answers to these. Okay? So just write out the integrals, and then you go to Wolfram Alpha, and you just have it do it for you. That just saved you about 3 hours right there.
on just this question or
On just that question. On just that question. That's number 6, right? That's what I've been told. All right, now, this section continues on. We talk about moments of inertia, and there's formulas for moments of inertia. The moment of inertia is very similar to the moment, except the moment of inertia about the x-axis, instead of putting just y, you put y squared. Moment of inertia about the y-axis, instead of doing x, you do x squared. And then you also have the moment of inertia about the origin, which is basically these two added together. I'm not going to ask you that on the take-home. I don't believe that's on the take-home, right? Moment of inertia. And that's it for that section. Now, we're going to call it a day, but I have some things to get back to you, and I have some comments to make. So we have now done how many take-homes? 3. Fourth one is due next week, or this Wednesday? Next week. Who wanted a copy of the test? Someone asked me about that copy of the test. You still need it? This is from the next class, the makeup, the take-home. Not the makeup take-home.
I just need to take a picture.
You can take one. These are all copies. So next class, what's due is test corrections on at least two problems, right? If you want the bonus points or the curve, you have to turn in 2 problems corrected. A third problem can be corrected for an additional 5 points on the test grade, right? That's due for everybody. And then mini exam 4 is due on Wednesday if you're doing it. You don't have to do it. So now that we've done these, here's what I'll say. I want you to think about this. I mean, like, the reason I do these exams is because I want you to start thinking about, like, your future in terms of working with other people. So, like, can you get your ideas onto a piece of paper in a way that people that you may work with one day can, like, understand you? Communicating your thoughts onto a page. That's part of what I want you to work on here, right? Because, I've told you, you're never trapped in a room where you don't have any resources. That's why I let you use formulas and cheat sheets. At the same time, you have to work with people. And if you're the only one who can read your work, like, that just doesn't work in the real world. You can't just, like, have a project, go turn it into your boss or to your colleagues and be like, hey, I've got some work, this is my work. And they all look at it, they're like, what the fuck? What is this? Like, I can't read any of this. Okay, so part of this is you being able to, like, organize your ideas, put them on paper. It's not, if I wanted this to be like a test like in class, that's when I expect things to be on the fly. You're just trying to get through the problem. You're just trying to understand it. That's one thing. This is a paper with proper punctuation type thing. I expect it to be written like it's presented. And the reason I say that is because I'm not going to call anybody out. I would love to call this person out because I'd like to just hand this to everyone, just say, like, this is what I mean. Okay, this is what I'm talking about. This is at least a page or 2 of work for each problem. Very well thought out. I can follow everything here, every step. I understand what's going on. Yes, there could be more, but it's enough for me to know what's going on. And then there's others where it's the test itself with the work crammed in between the lines. And like that to me that's not what I'm talking about here. So the instructions say, you must show all steps and justify your answers. Your work must be neat, in order, and stapled. I'm not just writing that on here just because I just want to write it. I expect it to be neat and legible. Okay, so please, these first 3 or 4 are okay, but like seriously, if you're going to do the last, 5, 6, 7, and 8, like I need to see some improvement on that because I'm getting to the point where I'm not motivated to grade them if I can't make sense out of them. And I want to give you partial credit, but I can't if I'm not following you. So something you can work on, I think. Yes. When it comes to things like integrals, like you need to show me. So I have, I'll have one student who did the integration by parts twice to get the antiderivative, or, did the limit and actually like did L'Hopital's rule to get the limit. Then I have other students who just go from this to the antiderivative and that's it. No steps, no work, nothing. You have to show your work. Okay? Unless I tell you otherwise, I expect it to be done. So like that problem with the one you asked me, number 6, center of mass, use Wolfram alpha to go get your integrals. Otherwise, everything else needs to be done pretty much mechanically. And I'm trying to stir up all the old calculus and algebra. I want it to, be fresh. You're finishing off the calculus sequence here. So I want you to actually bring it all back up, right? Okay. I hope that didn't seem I wasn't trying to be mean. I just trying to help you become better at communicating your ideas. I have